know Dr. Golomb. Basically, during this conference, also is Dr. Golomb's 75th birthday. So next tomorrow we have a banquet for him, conjunct with our workshop banquet. But his real birthday is today. So Miami ordered birthday cake for him for tonight's dinner. So Dr. Golomb did his shift register work at, I think, before the 1955, I think around the 1954, when he worked with the Golomb Martin Cooperation. Yeah, so then he realized the shift register sequences can be related to the polynomial ring. So then later on he wrote all of the results into his book, Shift Register Sequence book. So we all know it's the pioneer work in this area. So later on this type of work spread in many theoretical area, also the communications area, like all of the signal detection and synchronization, the code division, multiple access communication system. So this is all use pseudo random sequences. So in most of the theoretical books, then we're talking about the next linear recursive sequences. But in the all engineering textbook, they're talking about pseudo noise sequences. So that's originated from Dr. Golomb's work. And I think in Dr. Golomb, the book, in the last chapter, is talking about the Boolean functions. Maybe some of you haven't recognized. So this is a contemporary cryptographic concept we call the nonlinearity. So people rediscovered this concept in the late of the 80s. However, in Dr. Golomb's shift register book, he already discussed this concept. But he didn't call it the nonlinearity. He called it the invariance of the Boolean function. So I guess that people didn't make such a connection. Then they give another name called the nonlinearity. Then today, Dr. Golomb will talk about periodic binary sequences, solved and unsolved problems. Okay, please join me. Welcome, Dr. Golomb.
Well, I want to thank all of you for coming here today. We have people from as far away as Norway and Israel and Far East, and I'm very flattered that all of you have come. People in this audience include people that I've known for roughly 50 years from back at JPL. Quite a number of my former students and postdocs are here. Co-authors of papers, organizers of meetings that I've attended, and co-authors of books in a few cases. So I'm very flattered that all of you are here. And as Wang Gong suggested, I'm going to talk about something that I've been working on since the mid-1950s, and in a way this is a progress report on the last 53 years of my main technical work.
When's the final report, Saul? Saul? There will be no final report, right?
Yeah, I'm not sure there will be a final report. It's just an interim report. So the solved and unsolved problems that I want to discuss today are all motivated by the study of M sequences and their randomness properties. I should credit the term M sequences was coined by Neil Zeeler for the sequences that I was calling pseudo-noise sequences at the same time, but this is the name that has pretty well stuck. And by definition, an M sequence of degree n is a binary sequence obtained from an n-stage shift register with linear feedback that has the maximum possible period of 2 to the n minus 1. Here's a picture of a typical linear shift register with n stages, and each stage content is multiplied by a constant C1 to Cn. These are added mod 2. Some of this didn't print out too well from whatever computer language, but each of the stages is multiplied by a constant C1 to Cn. This is the binary case, so the constants are either 0 or 1. So another way of looking at this is you either do or don't add in the content of each stage in a mod 2 sum. And that sum is fed back to the left end of the shift register. Out of the right end, you get an output. And the first thing I discovered when I looked at these around 1954 was the way to study these is in terms of the what I call the feedback polynomial f of x, 1 plus the sum of ci x to the I from 1 to n. And this shift register produces an M sequence if and only if f of x is a primitive polynomial over df2, and that requires not only that f of x is irreducible over df2, but more precisely that f of x divides x to the t plus 1. If it wasn't mod 2, I would write x to the t minus 1 for t equals 2 to the n minus 1, and for no smaller positive values of t. So the first set of conjectures, unsolved problems, involves some of these polynomials. The total number of such primitive polynomials of degree n over df2 is known and easily shown to be the Euler phi function of 2 to the n minus 1 divided by n, because phi of 2 to the n minus 1 is the total number of primitive elements of this sort, and they occur n at a time in irreducible polynomials of degree n. So this is the number of primitive polynomials, and this is equal to the number of cyclically distinct M sequences of degree n. And historically, one of the things people have been interested in was finding M sequences where the corresponding shift register has relatively few terms that are actually added into the feedback function. So here are two of the strongest conjectures, still unproved. For infinitely many values of n, there are primitive trinomials, that is, functions f of x of the form x to the n plus x to the a plus 1, where a is between 0 and n. I would say the evidence statistically is that this conjecture is true, but I haven't seen anything that looks like a plausible attempt to give a proof. And another conjecture is that for all degrees n greater than or equal to 5, you can find a primitive polynomial with 5 terms. And again, I'd say the evidence that this is true is pretty overwhelming, but there is certainly, to my knowledge, no sign of anything that looks like it will lead to proof. Possibly the weakest conjecture of this type would be that there is some finite positive integer m, so that for infinitely many degrees, there is a primitive polynomial f of x of degree n having no more than m terms. The key thing here is that this is some bounded number that does not increase to n. And even if you could prove this for an outrageously large value of m, I believe that that would represent significant progress. And
is that going to stop it completely?
I would hope that that this conjecture is not out of reach.
Does this take the same amount of batteries as that one?
What I listed as conjecture 1 is the special case of conjecture 3, where the number of terms m is taken equal to 3. Conjecture 2 would imply conjecture 3 with m equals 5. If someone succeeds in proving conjecture 3 with a very large value of m, then subsequent work would be aimed at reducing that value of m to something nice and small like 5 or 3. I could even give a stronger conjecture than conjecture 1 that I would have no hope of seeing anyone prove in the next 50 years. That is that the trinomial, specifically x to the n plus x plus 1, is primitive for infinitely many values of n. I believe this is true, but I think this is on the same order as showing that there are infinitely many primes of the form n squared plus 1, things of that sort that seem to be beyond what anyone currently knows how to prove. Then the title of the talk, I mentioned solved and unsolved problems. Some 50 years ago, I observed from very limited data that I was never finding primitive trinomials or even primitive polynomials. Well, and specifically, I wasn't finding primitive trinomials when the degree was a multiple of 8. And A.A. Albert was running a summer program for many years called SCAMP, and he mentioned this as a hopeless problem. And Richard Swan, who I think was only a graduate student at the time, actually proved this conjecture in a slightly stronger form that x to the n plus x to the a plus 1, when n is a multiple of 8, always has an even number of irreducible factors. And since 1 is an odd number, the idea that this could be even irreducible, let alone primitive, is ruled out by Swan's theorem, which also rules out quite a number of other kinds of trinomials being irreducible. Here's something I can prove that I haven't published. If there's a primitive trinomial of odd degree n greater or equal 5, then there is also a primitive pentanomial, a 5-term primitive polynomial of degree n. I won't spoil your fun by telling you my easy proof of this, but I conjecture that this is true for even as well as odd values of n greater than 5, but I haven't found an easy proof of that, so I list as conjecture 5 that for all degrees n greater or equal 5, there's a primitive, if there's a primitive trinomial of degree n, then there's a primitive 5-nomial of degree n. And as another existing result, over 75 years ago, Einstein-Bohr proved that if this polynomial f of x is primitive, then this new polynomial, and I intended this to be a capital F to distinguish it from the original one, where we replace the exponent I by 2 to the I minus 1, that this new polynomial is irreducible, though not necessarily primitive. Of course, if it turns out that the maximum period or primitivity for degree 2 to the n minus 1 is a prime, then all irreducible polynomials are also primitive. So for certain cases, you would even get that the new polynomial is primitive when the previous one was. And there is this interesting sequence of Mersenne primes where each new one is 2 to the p minus 1 for the previous one, that goes 3, 7, 127, 2 to the 127 minus 1. And I don't think anyone has yet been able to test the next case. So this result has been independently rediscovered a number of times since, but this is certainly the earliest published reference that I'm aware of. Okay, now here are a number of randomness properties of the M sequences. And it's these randomness properties that make them useful in many applications of cryptography, radar, the GPS positioning system, and Monte Carlo techniques for seemingly random number generation, in code division multiple access cellular communication, where they still use these M sequences as their spectrum spreading technique. So if I consider all the sequences of ones and zeros with the maximum period 2 to the n minus 1 and degree n, the weakest condition that I would impose is simply that in each period of the binary sequence, roughly half the bits are ones and the other half are zeros. And since 2 to the n minus 1 is an odd number, I have to make these slightly unequal. So the M sequences have an excess of one more 1 than 0 in each period, and I call this the balance property. So that's the weakest condition that I consider. Then as more special cases, the run property requires that in each period that the average run length is 2, so there are 2 to the n minus 1 runs. Since runs of ones obviously have to alternate with runs of zeros, half of these 2 to the n minus 2 are runs of ones, and the other 2 to the n minus 2 are runs of zeros. But what I call the run property further requires that half the runs of each type have length 1, a quarter of the runs of each type have length 2, an eighth of the runs of each type have length 3, and so on. And finally, there is one run of each, I should say one run of zeros of length n minus 2, and one run of ones of length, I'm sorry, yeah, okay, there's one run of each, this is correct, there's one run of each type of length n minus 2, one run of zeros of length n minus 1, and one run of ones of length n. And this is sort of the expected distribution of run lengths when tossing a random perfect coin. The reason that I say sort of is if you actually got that distribution from a coin, you would suspect something weird is going on, because even what's called the perfect coin wouldn't give you that perfect a distribution of runs. This is sort of the ideal that you would hope for, but there's a dispersion around it. What Feller calls the law of the iterated logarithm, tells you something about the imbalance, even that you don't even have the equal distribution of zeros and ones exactly in a very large number of coin tosses. Another relatively weak property, well, this is a very weak property, a stronger property than this one, and that implies the run property, is the span n property. If you slide a window of length n around one cycle of the sequence of period 2 to the n minus 1, you see every n-bit binary number exactly once, except for the all zeros window, which will not occur in the M sequence. You see every other vector of length n exactly once. Another weak condition that the M sequences satisfy is the multiplier property, and that says if you take every second term of the sequence repeating around the cycle, since the period is odd, you go around twice, taking every second term to get a full 2 to the n minus 1 terms, you get back the original sequence, possibly rotated cyclically, but would consider cyclic rotations of the same sequence the same. It's also true that there is a natural starting point for the sequence, where if you start in that natural starting point and you take every second term, you get back exactly the sequence that you started with without any cyclic shift. So that's the multiplier property. And the stronger property that implies the multiplier property is the two-level autocorrelation property. And that says if you compare the sequence of period 2 to the n minus 1 with each of its non-zero cyclic shifts, you see 2 to the n minus 1 disagreements and 2 to the n minus 1 minus 1 agreements. Stated in correlation terms, if you define the autocorrelation function, C of tail of the sequence to be agreements minus disagreements divided by agreements plus disagreements. A sub tail is the number of agreements at a shift of tail. D sub tail is the number of disagreements at a shift of tail. Then you find that this normalized correlation is obviously 1 when there's no shift at all, but minus 1 over the period for all shifts between 0 and the period. This is these two values are why this is called two-level autocorrelation. There are other authors who call this perfect autocorrelation. The fact that this isn't exactly 0 makes me hesitate to use the term perfect. Here are some trivial examples. If you take the M sequence of period 7, 1, 1, 1, 0, 1, 0, 0, and you look at its successive shifts, and I've underlined where the agreements are, and for each shift there are exactly 3 agreements, and therefore 4 disagreements. So the agreements minus disagreements is -1, and divided by agreements plus disagreements, which is always the period, this is exactly -1/7 for each shift other than a multiple of the period. So if you plot the autocorrelation function, it will have a value of 1 at a shift of 0 and a value of -1 over p at every shift that is not a multiple of the period. And this property, among other things, makes these sequences ideal for use in radar, where you want this kind of correlation spike to indicate when the shifted sequence matches the reflected sequence matches the transmitted sequence. Stronger than any of the ones I've discussed before is often called the cycle and add properties, and this is not merely a property of M sequences, but it characterizes the M sequences. That if you have an M sequence and you add it term by term to any shift of itself other than the 0 shift, what you get back is simply a new cyclic shift. So I've illustrated that for the same sequence of length 7. Here I've shifted it by 1. If I add term by term mod 2, I get a new shift where the original 1 here now starts here. Shifting by 2, I get the shift starting here. Shifting by 3, the shift starting here. Shifting by 4, the shift starting here, and so on. That pretty much implies all the previous properties, but it's interesting that if I assume no more than that I have a periodic binary sequence, there's no assumption about even what the period is, that has the property that when added to each of its non-trivial cyclic shifts, I get back a new shift. That not only is implied by having an M sequence, but it implies that the period is 1 less than the power of 2, and that the sequence satisfies the linear recurrence relation that defines an M sequence. That's very easy to prove. The easiest way to prove it is by a vector space argument, that basically you're showing that the shifts of the sequence with the all 0 sequence adjoined form a vector space. And a vector space over the 2-element field has to have a size which is a power of 2, so the shifts, the total number of shifts, including the 0 shift, is 1 less than a power of 2, so that's how you get what the period is. And then in order for the period to be that, you can show that that every shift has to be a linear combination of the first n shifts, where the period is 2 to the n minus 1, and from that you get the linear recursion. So this is the fact that this is necessary and sufficient is not hard to show. Here is a simple relationship among the 6 properties that I described. Again, it's a pity that these labels didn't print out properly. This is the M sequences. This is the span N property. This is the 2-level correlation property. This is the run property. This is the multiplier property. And this is simply the balance property between 1s and 0s. In my shift register book, I give